Yeah, I think it changes the eye mostly. But would you recommend doing superposition to find deformation? Because that's the first, my idea is deformation. Because I know this is concrete, which means I have roughly this value. I
Yeah.
just don't think I'm waiting for this one, is this one for, because my team's making the airfoils.
Do you have a CAD model of it?
I'm a cat of their airfoil or their, because they haven't finished their airfoils.
Oh, okay.
So-
I was gonna say, you can just do FEA on it. That's probably the easiest thing.
I,
Because then you don't have to worry about any equations. Answer stuff report.
I want to do FDA. It's just, I know once I'm able to do this CAD model,
Mhm.
then I can do FDA. And it's just like running deflection.
Right.
Either way, I want to do hand calc to make sure it makes sense.
Oh, sure. Yeah, for sure.
I know how I'm gonna mount it, like, well, not how. This is, I'm still trying to figure out how I'm gonna drill it in and try to put a plate. But either way. I know once, I'll come to you probably like in a week or two, once this is confirmed,
Yeah.
because I'm gonna ask for help if I can run this in FEA.
Yeah, I mean, yeah, if you have a CAD model, probably can.
Okay. And I know what the boundary conditions are, it's just. That deflection.
Okay.
No, that doesn't matter. I'm in charge of the mounting. Owen and Isaiah are in charge of the wings.
I want to stay off topic. I was going to get a new Starbucks caffeine at the vending machine. I saw the the claw or whatever it is go up, lower a bit, go back with nothing in it, and it just took my money. I was like, all right, whatever.
Yes, oh,
I was so sad.
I would be sad too. Okay. Okay. I guess I'm just trying to find the conceptual questions.
Hmm.
Yeah. I'm trying to reduce this so it's just plug and play. Letting me get this. Okay.
Okay, let me write this down first, and then I'll
Oh, yeah, thank you. Either way, they plus. But I'll just take a photo.
I'm curious, what are the, what they're trying to do, like, the redesign?
So using the wing elements, I have to figure out the mounting. So this support structure, because the wings don't mount to the car, there's no downforce. Yes, there's no point of
Magnet, there you go.
magnet, no, there's no downforce settings for the car. So my first free body diagram was this one where finding the downforce where it is, which usually centered towards the quarter cord, and the weight is a little bit behind. I don't know the exact ratio because we don't have our airfoil selected yet, which is annoying me. But from here, I want to mount it here on the downforce because this thing downforce should be like for the rear wing, it should be like around 120 and it should weigh like 20 pounds. Yeah. So 60 times, 6 times. So
And like a big thing is to have it hold the weight without it interfering a lot with the,
that's, yeah, I mean, I can't really do much about that. I mean, if you look at the rear wing, it has a front roll hoop as a support bar and it has got either way.
and everything like that.
Either way, no, this is already set.
Oh, that's right, okay.
So dirty air is dirty air. My issue is assuming this force or this weight. And assuming on a mountain where the downforce is. How do I calculate this exact? Because I know it's a cantilever problem, but of course, having, because this is a fixed end. It has an arc to it. So the arc is already integrated, and I know this force is most likely downforce plus the weight. Because from this free body diagram, that's what you get. And there's no normal force because the normal force is what hits the screws. And that travels to this part, so technically this would be up, this would be down. That's how it translates. It should translate. I think, yeah. This should be normal there, so that's the only point of contact. Translates, this one's down force in the car. However, this deflection is only allowed 20 millimeters. Because the rules are only 25. So I want to have a 5 millimeter buffer in between, so in case like it's at 20, it can deflect up to 22 or down to 18.
That's my bad, that changed.
Yeah, my goal is 18 to 22, so it's within 25. My only issue is even with this downforce value, they can also add a force of 20 newtons in any direction, which could deflect it more. But 20 newtons is a lot. That's like. No, that's like 20 pounds. 162. Technically like 45 pounds in any direction.
Okay.
So I have to figure out how I can support, and this is one of the stack. So when it's static, this downforce value is 0 because there's no air, there's no downforce being generated. So it's only the weight in that. So it's, I'm not too worried about that condition.
We don't have the confidence.
My bad.
Okay, you got 20 more seconds.
I shall take photo.
I was like, ready for 9.
Helps me talk about it. Also, Sam Rockney did ask me, he's like, hey, where did Dr. Trump go?
Oh, yeah, I had to kind of jet real quick. Yeah, I didn't get a chance to say bye.
Yeah, and I was like, oh, he had to go see a friend, he's really sorry.
Oh, yeah. I'll follow up with you.
Turns out he does archery, I didn't know.
Oh. Bruno, so the license restriction that you're getting is based on the element count. And so you want to actually reduce the number of elements in your mesh. So if you're working on it at home, I think the element limit is 64,000. And so you want to increase the element size so that the number of elements goes down. Yeah. Okay, it's 5:30. Let's go ahead and get started today. All right, how's everyone doing today? Good, hanging in there. Good to hear. Good. Cool. All right, so today in FEA, we're starting something new. So, for the first 7 weeks of this semester, we've been focusing basically all on ANSYS, which is good, which is great. We've done a lot of cool ANSYS stuff. You guys have a mission project. But, this class is not just an ANSYS tutorial class. And so we have to do a little bit of theory, you have to do a little bit of kind of background info on FEA. Just because this is technically introduction to FEA. So for the next few weeks, we will be covering some of the background theory of FEA, starting with a method called the direct stiffness method. Okay. So today the plan is just introduce this method, kind of see what it's all about, and see how it relates to FEA. Okay. Because it's one thing to to know how to use ANSYS and to kind of use it well, but if you're going to be taking a class in FEA, you should understand a little bit of how ANSYS kind of works underneath the hood, right? Because there's a lot of actually really interesting math, a lot of really interesting algorithms and theory that goes into what you see as kind of a really nice software like. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and begin. Okay. So the topic for today is called the direct stiffness method. Okay. So let me start by saying that, the finite element method is kind of a very general methodology, a very general kind of approach to problems. There's lots of different ways to implement this method, right? So ANSYS does one implementation, direct stiffness method is another, okay? We're not going to get too much into the weeds in terms of, what the different implementations do or what an implementation really means. The only reason I bring it up is to say that, what we're going to cover with the direct stiffness method is not exactly what ANSYS does, but it's about maybe 80% similar. Okay, so a lot of what we're going to go over ANSYS does a lot of similar things, but just a lot of the details of the algorithm are not, the same. Okay. But the whole point of going through this is so that you can kind of get a better understanding of kind of what's happening within ANSYS, within the computer, when you do the mesh, when you do the boundary conditions, when you solve the problem, this is kind of what it does. Okay. Okay. The main thing that I want you to take away from the direct stiffness method is how we can take a physical problem, a physical analysis problem where we're interested in things like deformation, deflection, stress, things like that, how we can go from that to an algebraic problem. Okay. And really that endpoint is the key, right? And so finite elements is not the only computational methodology that's out there. So there's also finite volumes, there's also finite difference, right? You may have had some experience with these in your previous classes, but they all kind of have the same goal, is to take kind of a very complicated physical problem, or sometimes in a very complicated math problem like a differential equation, and transform it into an algebraic problem. Okay. The reason we want to do this is that, computers are really good at solving algebra problems. Okay. Even massive algebra problems. So, typically, when you think of an algebra problem, from your previous linear algebra class 250B, you may be thinking of, 3 equations, 3 unknowns, or maybe 5 equations, 5 unknowns. But, the types of linear algebra problems that can be solved with a computer are things like, 1 million equation and 1 million unknowns, right? And so that's actually not that bad for a computer to do. Okay. So they're massive. And so, these algebra problems don't have to be in a particular form that you can solve by hand, but the point is to get it into an algebra problem. So that's kind of the point of, it's the point of the direct stiffness method, but it's the point of the entire kind of finite element method in general. Okay. And again, the direct stiffness method is just kind of one implementation. Okay. The reason I teach it, right, and the reason I kind of stick with the direct stiffness method over other finite element implementations is that it has a very physical kind of intuition, very physical kind of understanding of how it works. Okay. Okay. It's very intuitive, very physical, but at the same time, it still respects kind of the general finite element, methodology. Okay. And so most importantly, the direct stiffness method is going to illustrate what I consider to be kind of the 3 critical steps of the finite element process. Okay. Step 1 is to generate what's called the element stiffness matrices. Step 2 is to do a step called assembly. And step 3 is to apply boundary conditions. Okay. So technically, the finite element process has more steps than this. You have to do your mesh, you have to solve the system. But these are the 3 kind of, I would consider to be the critical steps. Okay. So out of these 3 steps, probably the only one that kind of looks familiar to you is step 3, the boundary conditions. Okay. And so the element stiffness matrix and assembly, we'll go over what that means today. But for the most part, ANSYS kind of handle those things for you. But again, it's kind of important to know kind of what ANSYS is doing with those steps, that you have a better appreciation. Okay. All right. So let's go ahead and get started. So we'll dive into kind of each step of this process, and we'll talk about kind of what each one means, right? So the one that we're going to spend the most time on by far is the element stiffness matrix. So let's start there. Okay. Okay. Stiffness matrix. All right, so remember, the goal for finite elements is to take a physical problem or a complex math problem and to form it into an algebraic problem. Okay. I think nothing really kind of illustrates this better in the finite element process than the stiffness matrix. Okay. Basically, the idea with the stiffness matrix is to form an algebraic connection between the applied forces or external effects and the system response or the system deformation and stress. Okay. Okay. Because those two things are kind of the main inputs and outputs of a finite element simulation. So to think of kind of what we've been working on in ANSYS, right? The applied external effects would be like your boundary conditions, your forces, your fixed constraints, and the response are things like the deformation and the stress. Okay. So what the stiffness matrix aims to do is that it aims to form an algebraic connection between these 2 entities, so that we can kind of solve it in the computer. Okay. And the reason it's a matrix is that, a matrix is used often to represent an algebraic system, right? So let's say that you have a system of linear equations. Okay. So let's say that, I have, three unknown variables, x1, x2, x3. So let's say we have 3x1 minus 4x2 plus 7x3 is equal to, I don't know, 14. Okay. That's one equation. Maybe we have another equation, maybe minus x1 plus 2x2 minus 9x3 is equal to 24. Okay. We need a third equation. My creativity muscles are gasping for breath right now, trying to come up with random numbers here. Okay, so let's say we have 2x1 plus 7x2 minus 3x3 is equal to 18. Okay. So we have a system of 3 equations and 3 unknowns, right? x1, x2, x3 are unknowns, and our 3 equations there represent the relationship between them, right? Now you can solve this system. So, because it is a system of 3 equations and 3 unknowns, theoretically, we should be able to solve for all 3 values for x1, x2, x3, okay? Now, I'm not interested in that right now. That would kind of take too long for me to do, especially just because I made up all these numbers just, on the fly. So, the answers may not be very nice. Okay. Let's do it by hand just for fun. Yeah, maybe after the lecture. Yeah, we'll have more time. But the whole point of this is that, you can take a 3 by 3 system like this and you can extract a matrix of coefficients, okay? And so if I take every coefficient in front of each of the variables here, right, so all these numbers here, we can go ahead and plug that into a matrix, okay? Okay. So our first row in the matrix is going to be all the coefficients on the first row. So that's 3 minus 4, 7, okay? Minus 1, 2, minus 9. There you go, 2, 7, minus 3. Okay. That matrix is then multiplied by a vector of our unknowns. We have x1, x2, x3, okay? And that equals the right-hand side vector. Okay, so this is 14, 24, and 18. Okay. So in this situation right here, this matrix here, one way that you can interpret this matrix is what is going to relate. It relates our unknown variables, x1, x2, and x3, to the right-hand side vector. Okay. If you've never seen the term RHS before, RHS stands for right-hand side. Okay. Okay, so that matrix there kind of formed the critical link in between those two, right? And more importantly, because this the origins of this was a set of algebraic equations, that matrix forms an algebraic relationship between our unknown variables and our right-hand side vector. Okay. And so our stiffness matrix, what we're going to do with that is that it's going to form the exact same goal. Okay. But for our stiffness matrix, we're going to have a linear system like this, right? But the things that we're going to be relating is that this is going to be our vector of unknown system response. Okay. So that's usually the unknowns in a finite element simulation. So that are things like deformation, the stresses, and so on. Okay. And then on the right-hand side, this is usually where we put our boundary conditions. And so, any kind of, external forcing, external loads, any kind of fixed constraints, all external effects usually go on the right-hand side of the algebraic system. Okay. So that's kind of a little bit of a preview of kind of where we're going. So eventually, through the stiffness method, we're going to form an algebraic system like this, where we have a vector that is going to contain our unknown solutions. So our unknown deformations, our unknown stresses. We're going to have a vector of known boundary conditions, right? So that's going to be on the right-hand side of the system. And then what's relating these two things is our stiffness matrix in between, okay? Okay. So in other words, we need to be able to derive this, right? So we need to be able to come up with expressions that's going to give us this exact matrix here. Okay. So the challenge here is, how can we come up with this? For physical systems. All right. Any questions on this so far? Okay, good. All right. So let's see how this works. And we're going to start with something that is hopefully very familiar to a lot of people, and that is a simple spring, Hooke's law. Okay. Okay. So a simple spring, let's say that we have a spring that's fixed to a wall. Okay. This spring can be, we'll say that we're going to pull on the spring with a tensile force F. Okay. And then as a result, the spring is going to deform. Okay. So this D here is the change in length of the spring after the force is applied. Okay. So we can relate these two quantities, right? And so according to Hooke's law, and oh, I forgot to say, the spring, we'll assume that the spring constant for the spring is known. Okay? So the spring has a constant of K. And so according to Hooke's law, F is equal to K times D. Okay? Where F there is the applied force, D is the resulting deformation, and K there is the stiffness constant or spring constant. Okay. So here we have a very simple kind of algebraic equation or algebraic relationship between, the force that you apply on the spring and the resulting deformation. Okay. If you look at this equation and we compare it to our, algebraic system that we have up here, right? It looks pretty similar, although I kind of reverse, I kind of put the force on the opposite side, right? And so very similar to our equation up here, we have some kind of external effect, right? So our external effect here is the external force. We have the resulting deformation. So the resulting deformation is the same as the system response, right? So the way that the spring is going to deform, that's the way the spring is going to respond to the external force, okay? And then we have the algebraic, mechanism that relates the two, okay? So for a simple spring, we don't have a matrix, but we just have kind of one constant here, which is K, right? So that K right there kind of is going to play the exact same role as our matrix, right? So that K there represents the relationship between an external force and a system response, okay? Okay. So that equation there is relevant for a one-dimensional spring. So a spring that's fixed on one end and we just pull it on the other. Okay. What if we take our spring and what if we change it so that we have 2 degrees of freedom instead? Okay. So instead of being fixed at the wall, both ends of the spring are now going to be free to deform or stretch. Okay. Let me go ahead and draw a spring. It's now freed from the wall. And so now the left-hand side of the spring will deform with an amount D1. Okay. And the right side of the spring is going to deform by an amount D2. Okay. I'm drawing both in the positive direction for now, just because, you know, just for convention. But just know that, you know, the D1s and D2s can be negative as well. Okay. Okay. And so we can also apply forces on each side of the spring as well. Okay. So let's say that on the left side on node 1, we're going to have the force F1. Okay. And on the right side, we're going to have a force F2. All right. So let's do the same thing we did above. So let's form a relationship between our two system responses, so our two D1s, D2s, and F1 and F2. Okay. All right. So that relationship is, you know, because we have multiple variables here, we're going to need a matrix for that. Okay. So now we have, well, let me draw it like this, just so it's similar to what we had above. Okay. So here is our stiffness matrix. Okay. This is going to be multiplied by our system response. So this is multiplied by the vector D1, D2. And that's going to be equal to the nodal forces F1, F2. Okay. Okay. And so now the goal is to say that, you know, how are we going to determine the entries in this particular stiffness matrix? Okay. So from this matrix here, you can see we have 4 entries to cover. Okay. We have this entry, this entry, this entry, and this entry. Okay. So we need to determine what those values are going to be for a particular spring. Okay. All right. Any questions on this so far? Okay. All right. So let's get to work kind of finding out what those values are. All right. So to find out what those values are, you know, we have to kind of remember that this matrix set of equations basically represents 2 algebraic equations, right? So we have 2 equations for our 2 unknowns. Our 2 unknowns being D1 and D2. Okay. And so one way that we can find out what those entries in the stiffness matrix is to you know, write out what these algebraic equations are based on the physics of the spring. Okay. Okay. So let's take our spring. So even though, you know I drew up here, you know, I drew kind of the most general case up there, where each end of the spring can have a general force and each end of the spring can have a general deformation. Okay. Let's just kind of isolate just one particular spring. Okay. You know, in other words, let's take a spring that's in static equilibrium. Okay, so a spring in static equilibrium is going to have an equal and opposite force on both ends of the spring, right? Because in order for the spring to be, static and not moving, the sum of all the forces on the spring have to equal 0. Okay. Okay, so let's draw our spring here. Okay. And so to be in static equilibrium, let's say that we have a tensile force T being applied on the right-hand side. Okay. In order to cancel that out, we have to have an equal and opposite tensile force applied on the other side. Okay. So we again have K in the middle here. So K is the spring constant of the spring. Okay. And then just like we have above, we're going to say D1 is going to be applied to the right. Okay. And this time we have D2 being pulled over to the left. Okay. So that makes intuitive sense. And so if we take a spring, we pull on it with the tensile force, right? As long as the forces are equal and opposite in both directions, the spring is going to stay static, but the spring itself is going to deform, right? And so it's going to stretch, based on the amount of force that we apply and the spring constant of the spring itself. Okay. All right. So let's use this particular situation here to determine, what are the entries in the stiffness matrix. Okay. So let's use Hooke's law, right? So let's use kind of the basic kind of spring equation that we had above to relate our tension T to our variables D1 and D2. Okay. And so according to Hooke's law, the tension that we are applied on the spring is equal to K. We're going to multiply by K multiplied by the total amount of stretch of the spring itself. Okay. Now, the total amount of stretch that the spring undergoes can be computed based on the deformations of the ends. Okay. And so one way that we can do this is we can say that T is equal to K times D2 minus D1. Okay. So this right here is the total stretch of the spring. Okay. All right. So this equation right here, kind of represents the physics of this particular spring, right? It relates the applied tensile force and it relates it to the deformation. Okay. Let's take this result. And let's take this result and apply it to our 2-degree of system spring above. Okay. And just so that you don't have to scroll up and down, I'm going to go ahead and draw that general spring again one more time down here. Okay. And so that general spring look like the following, right? The general spring had a D1 in this direction, D2 in this direction, okay? And most importantly, we had general terms for the nodal forces, right? So we had F2 on this side and F1 on that side, okay? Okay. All right, so let's take this equation here and let's come up with expressions for F2 and F1 based on what they represent in the static situation. Okay. And so if we look at the directions of this spring here, we can see that, F2, right? F2 should have the exact same magnitude as this T up here, right? So F2 there represents the force that's applied on the left node, okay? But the only difference is that F2 is pointed to the right and T is pointed to the left. So that means F2 must equal to minus T, okay? So it has to go in the opposite direction, okay? And then F1 is the opposite. So F1 has the same magnitude as T, but F1 and T in this case both go to the right, right? So in this case, F1 is equal to T, okay? And I'm realizing I have a slight typo here. I apologize. So actually, this equation up here, well, I'll correct it down here, okay? Okay. So now that we have these expressions, let's plug in for T. Okay, because we have an equation for T up here. Now this equation for T is a little bit, there's a small mistake here, but I'll correct it down here. Okay. So F2, okay, based on our equation for T up there, F2 should be minus K. And then I'm going to make this correction here. So it should be D1 minus D2. I apologize for that. Okay. So let me just go ahead and point out these were swapped by mistake above. Okay. So I apologize for the confusion, but these, the equation there should be D1 minus D2. Okay, for T. Okay. And then F1 here, we're gonna plug in for the exact same expression for T. Okay. And so if we plug in for T with the corrected version, it should be K times D1 minus D2. Okay. Okay. So now that we have it like this, we can put these two equations in, we can put them in matrix form. Okay. So our first equation, F1 is equal to K times D1 minus D2. Okay. Our second equation, F2. So I'm just gonna distribute that negative throughout. And so this can be equal to K times minus D1 plus D2. Okay. So now that we have these two algebraic equations for our two unknowns, D1 and D2, we can put it in matrix form. And then that resulting matrix is going to be our element stiffness matrix for the spring. Okay. Okay, so putting this in matrix form, we have F1, F2, okay, as a vector. That's equal to our matrix here. So our matrix here is going to be K, minus K, minus K, and K. Okay. Multiplied by the vector D1, D2. Okay. Or this right here is our element stiffness system. Okay. And this matrix here, this right here is our element stiffness matrix. It's our element stiffness matrix for a single spring. So pretty straightforward. So it's just different combinations of the spring constant. It's just they're going to be positive on the main diagonal and negative on the off diagonal. Okay. All right. Any questions on how we got to this point here? Okay, good. All right, so this system right here represents the system for a single spring, but a single spring by itself usually isn't that interesting, right? So a single spring, you can usually solve it by hand, right? The whole point of using finite elements is to kind of combine together a lot of different elements together and see how that works. Okay. So let's see how that works when we have a multi-spring system. Okay. Let's talk about assembly of multi-element systems. Okay. So I'm going to do this exam, or I'm going to show you this kind of through kind of a very kind of walkthrough example. So let's do an example here. Okay. Just to kind of show you that you can use the results above. So even though the results above are only for a single spring, they actually form a critical piece to, solving a multi-element, multi-spring system. So let's look at a two-spring system. Okay. So let's say that we have a wall that's fixed on the left-hand side. Okay. Let's say that we have one spring here, so we'll call this spring A. Okay. That's going to be attached to another spring. We'll call that spring B. Okay. So the spring constant for spring A is Ka. The spring constant for spring B is Kb. Okay. And then we're going to be pulling on this entire system with a single force F. Okay. Those of you who are coming from optimization, this might be a little traumatizing. I understand. We're solving it in a completely different way. We're not using optimization for this. Okay. All right, so we need to label the nodes in the system. So the nodes are just the ends of all the springs. We have three nodes here. So we have node one that's going to be attached to the wall. We have node two that's going to be right in between the two springs. And then node three on the right-hand side where the force is applied. Okay. And then in each of the nodes, we can compute how much the entire system is going to deform at each of those nodes. Okay. So we have three unknowns in the system, D1, D2, and D3. So we want to use this system and use it to compute D1, D2, and D3. Okay. And so if we have three unknowns, that means we have to have three different equations. Okay. And so if we have three equations, that means we're going to have a 3x3 system. So three equations, three unknowns, and our matrix is going to be 3x3 as well. Okay, so our system is going to look like this. So we have our 3x3 stiffness matrix. Okay. We have our unknown variables, D1, D2, and D3. And then we have our forcing vector, F1, F2, and F3. Okay. Now the question is, how are we going to find this 3x3 stiffness matrix? So we've determined the stiffness matrix for a single spring, right? So that's no problem. But we don't have a single spring here. We have two springs. Okay. So the question is, how can we take these two springs and, use it to together form the stiffness matrix for the entire system? Okay. It turns out that to find this stiffness matrix here, this big one, okay, this 3x3 stiffness matrix is going to be formed through a combination of all the individual stiffness matrices for each individual element or each individual spring. Okay. So in other words, you can form, I call this kind of the system matrix or the system stiffness matrix or the global stiffness matrix. And you can find it through a combination of all the individual stiffness matrices. Okay. And that idea that you can take, a very complicated system with lots of different elements and just combine together all the individual element stiffness matrices for all the individual elements is kind of a key core kind of idea of finite elements in general. Okay. So we're doing a very simplified form of it here. We're doing a simplified form with just two springs, but you can imagine that this process that we're about to go through is generalizable to your finite element meshes and ANSYS that have 1,000, 10,000, 50,000 elements. Okay. Of course, ANSYS just does it on a much grander scale, just because it's you just have way more elements. Okay. All right. Any questions on this before we get started with solving the problem? Okay. All right. So we have our strategy, we have our algorithms. Let's go ahead and execute. Okay. Okay, so step one here, let's write out the individual element stiffness matrices for element A, spring A, and spring B. Okay. So for spring A is connected to nodes 1 and 2. So what we can say is that we have KA minus KA minus KA, KA. Okay. That's multiplied by the vector D1, D2. Okay. And that's equal to its forcing vector F1, F2. Okay. All right. So knowing which nodes are attached to the elements is actually going to be really, really important. That's how we're going to assemble it. Okay. Now for element B, okay, element B is connected to nodes 2 and 3. Okay. And so element B, our element stiffness matrix here is going to be KB minus KB minus KB, KB. Okay. Now, since element B here is connected to nodes 2 and 3, we need to make sure that's reflected in our element stiffness matrix, okay? And so instead of multiplying by the vector d1, d2, this is going to be multiplied by the vector d2, d3. d2, d3 equal to f2, f3. Okay. And just to complete this, let me say element A element A is connected to nodes 1 and 2. Okay. So now that we have the individual element stiffness matrices, let's assemble these into one kind of big system. Okay. So let me go ahead and write out our global stiffness system again. Okay. So our global stiffness system is a 3x3 system here. Okay, so we have D1, D2, D3. And on the right-hand side, we have the vector F1, F2, F3. Okay. Now we're not going to do anything with the F vectors just yet. So we'll deal with that when we apply boundary conditions. But the first thing we need to determine is, how are we going to fit our two matrices there? How are we going to slot it into our big system here? Okay. Okay. All right. So the key to this assembly process is knowing which nodes are connected to which elements. Okay. So let's take node element A, right? So element A is connected to nodes 1 and 2. Okay. So let's take the entries for element A and let's slot it into all the spots in this matrix that have to do with nodes 1 and node 2. Okay. So what we want to do, slot in. We're going to slot this into spots that have to do everything that has to do with nodes 1 and node 2. We're going to slot this element stiffness matrix into those spots. Okay. And to help you out, let me add some extra labels here. Okay. So based on the system that we have right now, we can see that the first row is kind of you kind of consider it to be the D1 row because the D1 is labeled there. The second row is the D2 row. The third row is the D3 row. Okay. Now you can actually label the columns in the same way as well, right? And so the first column is going to be D1. The second column is going to be D2. Third column is going to be D3. Okay. And remember, the reason it's like this is because remember those columns there, or I would say each entry in the matrix represents a coefficient of our linear algebraic equations. Okay, so we can label the columns in the same way. Same thing for our element stiffness matrices as well, right? And so for element stiffness matrices for element A, the first column is going to be D1, second column is going to be D2. Okay. For element B, the first column is going to be D2, the second column is going to be D3. Okay. Okay. And so with this knowledge, right, we can see that element A is going to be acting on nodes 1 and 2. Okay. So let me do this. And so all the entries here in this big stiffness matrix that have to do with nodes 1 and 2 is everything in this kind of top left corner of the matrix right here. So I'm going to draw kind of a dotted box or dotted line around all of those entries. Okay. So this is everything with element A. Okay. Element A does not interact at all with node 3. And so there shouldn't be any intersection with element A and node 3, right? So element A is only interacting with node 1 and node 2. Okay. Okay. And if you look at the space that we've drawn out here, this space is a 2 by 2 space, right? So we have 2 rows and 2 columns to this space right here. Okay. That's perfect because if we look at our element stiffness matrix, our element stiffness matrix is also a 2 by 2 matrix. So let's go ahead and slot those entries in the exact kind of way. And so you can almost think of this as basically just, you're taking this matrix here, you're hitting Control C on your keyboard, and then you're moving into another part of your document, and you're just doing Control V, right? So copy and paste. Okay, so if we copy and paste that in there, we get KA minus KA minus KA and KA. Okay. All right, any questions on how we slotted this this element stiffness matrix in here? Okay, good. All right, so let's do the same thing for element B. So element B, we're gonna do the same thing. We're gonna slot it in, but we're gonna do it on a different area because element B here acts on nodes 2 and 3. Okay. Okay, so just like we did with element A, let's box out a section of our global stiffness matrix here that is interacting with nodes 2 and 3. Okay. All right, so that section is going to be this one right here. Okay. Element B does not interact with node 1, so any row or any column that has to do with node 1 should not be included with element B. Right? So element B only interacts with nodes 2 and 3. Okay. And then we're going to do the same thing. So we're just going to copy and paste all the entries for element B into this area that we boxed out in the global stiffness. Okay. Okay. So obviously, we have one entry there that's overlapping, and I'll talk about what to do when you have an overlap in a second. But let me fill in the other parts first. Okay. So all the other entries without an overlap, we're just going to fill in those entries just like that. Okay. Now, when you have an overlap, right? So when you have entries of your element stiffness matrices that overlap each other, what you do in those cases is that you simply add those entries together. Okay. So we're gonna have KA, since this overlaps with an entry in element B, that entry is gonna be KA plus KB. Okay. Okay. Now, there's some spaces that we have to fill in. So not every space in the matrix here was taken up by an element stiffness matrix. Okay. Whenever you have spots that are unfilled, so that don't have any entries, that aren't associated with any elements, then you're going to fill in a 0 for those entries. Okay. So here we have 2 zeros, and so we have a 0 in the 3rd row, 1st column, and then a 0 in the 1st row, 3rd column. Okay. So any entry that's not covered by an element stiffness matrix, you simply just put a 0. All right. So this looks really good, right? And so our goal from this process was to take our spring system here, right? So we have a system of 2 springs, right? 3 unknowns. And we wanted to form an algebraic equation of 3 equations and 3 unknowns, okay? And so through this process of assembling the element stiffness matrices, we got just that, right? So what we have here is our 3 algebraic equations for our 3 unknowns, D1, D2, and D3, but it's in matrix form, okay? And so theoretically, right, we're now at a point that we can solve for D1, D2, and D3. Okay, right? Because the rules of algebra state that, if you have the same number of equations as unknowns, that's enough to solve the system, right? So why did I put a question mark there? Well, you could say that the question mark is there for a few different reasons, right? So on the one hand, even though we have the left-hand side of this matrix, it looks mostly good. If we look at the right-hand side of this matrix, we still have these generic F1, F2, and F3, okay? So those are still undefined. Okay? We haven't specified those values yet. And so, we can't really solve the system until we assign something there, right? We can only have one unknown vector. So the only unknown vector that we can have is D1, D2, and D3. And so right now in its current state, we can't solve it because we haven't put in numbers for F1, F2, and F3. Okay. So that's probably the main thing. That's probably going to be the main thing that prevents from solving this system. Okay. But another reason that you can't solve this system, it's a little bit more subtle, although just as important, is that we have we have a symmetric left-hand side matrix. Okay. And if you don't remember what a symmetric matrix is, if you draw a diagonal line right down the main diagonal of the matrix, right? And if you consider that diagonal line to be a mirror, right, you can see that the 2 halves of the matrix, when cut this way, are identical to each other. Okay, so we have a symmetric matrix. Turns out when you have a symmetric left-hand side matrix, or that left-hand side matrix that represents a system of coefficients for a system of equations, you're not able to solve the system. Okay? This system is what's known as well. I think the better way to say is that the condition number of this matrix is 0, or the determinant of the matrix is 0. Okay. Okay. Now, the way we can fix this, the way that we can make this system solvable is, first of all, we need to apply boundary conditions to define our F terms. But the boundary conditions actually serve a second purpose. The second purpose of the boundary conditions is to modify the left-hand side matrix to provide enough constraints so that we can solve this problem. Okay. So both of those things can be solved by the same thing, right? So defining a right-hand side vector and making our left-hand side matrix constrained, both of those issues can be solved by applying our boundary conditions. Okay, and so that's the next step that we're going to do. Okay. All right, any questions on this so far? Okay, all right, so we have about 10 minutes left, and so I think that's enough to kind of go over or start the boundary condition section, but we're probably going to finish it up on Thursday. Okay, so let's start. Okay. So, boundary conditions hopefully doesn't need any introduction, right? So we've been doing boundary conditions a lot in this class. So boundary conditions we know just represent any kind of external effects that are affecting your physical system, whether they be, constraints, fixed constraints in some way, or maybe some kind of external limits. Okay. The only difference now is that we have to learn how these boundary conditions can take a mathematical form for us to use it in our stiffness system. Okay. So before, with the boundary conditions, we didn't really think about its mathematical form. We just applied it within ANSYS itself. Okay. So remember, we made the distinction between constraint type boundary conditions and load type boundary conditions. Mostly just for the purpose of, kind of explaining what they do in ANSYS. But, we're going to kind of expand on that definition a bit more, just so that you can see how they mathematically affect this system. Okay. So just as a reminder, there are two types of boundary conditions. Okay. So we have constraint type and load type. Okay. And so how these types of boundary conditions are treated in the stiffness system are different. Okay. So I'm actually going to start with the load type, because the load types are a little bit easier. Okay. Okay. And in particular, I'm going to start with a very particular type of load type boundary condition, which is a force that's applied on a node. Okay. Okay. In other words, like a nodal force. Okay. So of course, there are a lot of different types of load type boundary conditions that you can apply. We've done so many of them already in this class, and so you can apply things like pressures, distributed forces, moments, torques, and so there's all different kinds of load types. Okay. Now with our direct stiffness system, we are kind of limited in terms of the types of geometries that we can do, and so for now, all of our load type boundary conditions will be nodal force boundary conditions. Okay. All right, and if you look back at the example that we were doing, that's kind of exactly what we have. Okay. And so if you look at our system here, this is where we started. We have one load type boundary condition in this case, and that is applied on node 3. Okay. And so you can see on node 3 here, we have a nodal force F being applied only on node 3. Okay. In other words, what you can say is that the force that's being applied on node 3 is equal to F, right? So in equation form, we can say that little f3, so little f3 represents the force that's being applied on node 3 is equal to F. Okay. Let's apply that equation to our stiffness system down below. Okay. All right, so now that we know, so let's kind of etch this into our brain. So little f3 is equal to F. Okay. Let's come back to our stiffness system here. Okay. Let me just kind of erase all these red lines here. Okay. So what do we know? We know from above that little f3 is equal to F. Okay. Do we see a little f3 in this system here? We do. Little f3 is right there. Right? And so applying a nodal force boundary condition is actually very, very simple. And so all you have to do is just locate the node where that force is being applied, and then just insert that into the right-hand side matrix. Okay. So there's no modification of the left-hand side matrix that's necessary. You just kind of take the load and just plop it right into the vector. Okay. And so if we do that, we plop this right in. I'm just going to erase F3 and then just replace that with F right there. Okay. So that right there is our external load that's being applied. Okay. So to kind of summarize that, if you have a load type boundary condition and nodal force, applying this is very simple. And so to apply this to the global stiffness system, okay, right? All you have to do is just stick that nodal force into the appropriate row of the forcing right-hand side forcing vector. Okay. And so that's exactly what we did for this example here. So we just plugged in, we know that we have a force with the magnitude of F applied on F on node 3. And so we just replaced little f3 with big F. Okay. Exactly kind of what we did right here. Okay. Now you have to be careful here. And so it's not just plugging in the magnitude, you have to be careful of the sign as well. Okay. Okay. And so in our particular example here, the force F is being applied, it's going from left to right. And so that's in the positive X directions. That's why we applied a positive F. But if the force were, pointing to the left, and so pointing in the negative X direction, we'd plug in a negative F into our global stiffness system. Okay. All right. So that's kind of one mistake I kind of see people make lots, using kind of the opposite sign. We're just using positive. Okay. But you want to make sure you use the right signs. All right. Any questions on this? Okay, all right, so we're just about out of time. And so when we come back on Thursday, we'll go over constraint type boundary conditions and how to apply those. Those ones are going to be a little bit more complicated. So those ones are going to be take a little bit longer to explain. And then we'll do one more example to kind of nail this whole thing down. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you all on Thursday. Yep. Yep.
Yeah. We did that one part. So first thing you should check. The other thing that could possibly happen is that fully, let's look at the slide. Okay, so that road to. Okay, it's one thing. Pretty sure. Oh, okay. So your displacement boundary condition right now is being applied to the same side. Want to actually fix it on. I'm going to do this. Okay, why? Well, we can do the same thing. But you want to make sure that you do it on the top. Right now, all the big supports are right there. I think what's happening is that you're applying a force on the position. Okay. Well, oh, right. You know, why? Like that. Yeah. Oh, looks like, so you're trying to find a connection with this edge of the road. But there's still kind of a thing. Okay, so I think what may have happened when you were working, probably need to extend the road one more time. Looks like there's nothing there. But we see how there's. So this connection right here, so these two connections are not able to come. So it may be fixed, but you may go back in space and it extends. So that will kind of extend it over here. If it's not, if it extends out, you may have to. Yeah. I think that's the major. I anticipate get hot. But I am getting. But overall, yeah, well, it looks like it's probably better. Because if you want like Air Force or planes for a car, kind of like, bro. I was like, I feel like if I like sorry the word out of the question, how much trouble. You just wouldn't work the second part. I'm regretting that too. I should have just taken the front. I thought yeah. But every time you click, like change the if you look at the word, oh, I didn't forget it. I just easily. So it looks like you're off by this one. So I was giving you the road. I was leaving the road up. I would move the road up, maybe about 24. A little bit more. And then shifting higher.